Hi, so we're starting chapter 5 today. So, chapter 5 is not as meaty as chapter 3 and 4 were. Chapter 6 will get a little bit more meaty, and we get meatier and meatier as we go. Chapter 5, we're talking about probabilities. This first section, chapter 5 or section 5.1, will probably not be too long. So, we're going to be computing and interpreting probabilities using the empirical method and computing and interpreting probabilities using the classical method. And we're going to do that, and then we will have some fun with it in 5.2. So let's just start right away. So when we roll a dice, there are 6 different possibilities. You can roll 1, 2, 3, 4, 5, or 6. So we're going to talk about the what that looks like, what the notation is. And I'm basically going through some of this notation because it's in the book, but I'll let you know the pieces that you won't, you'll never be asked to replicate. You might see it on one of the online homework assignments, but I'm not going to ask you to replicate it. So let's start with identifying outcomes of a probability experiment. So outcomes are basically all of the possible things. So we're not looking for the probability of one thing happening. We're looking for all of the possible outcomes. Oops. So what are all of the outcomes? So this is the notation the book gives. I don't require you to write it out like this, because could you imagine if I asked what all of the outcomes were for pulling cards out of a deck of cards? You would have 52 of these. So we have a lowercase e with a sub number, so sub 1. So E sub 1, E sub 2, E sub 3. So this is just listing individually all the different outcomes. I'm not going to ask you to list them like that. I'm perfectly fine with you just giving me a list with commas between them. So if I asked you for the outcomes, I'm perfectly fine with you just saying rolling 1, 2, 3, 4, 5, or 6. I'm perfectly fine with that. And I would not ask you to list all of the outcomes of a deck of cards. That would be terrible. So determining the sample space. So sample space is all of the possible outcomes. I'm having a hard time getting it to go to the next screen. So all of the possible outcomes, and we write it in set notation. So you might remember hearing set notation a while back in one of your earlier math classes. So this is what set notation looks like. And yes, I do want you to write them out like this. I'm not going to ask you all the possible outcomes, or I'm not going to ask you what your sample space is for a deck of cards, but I might for rolling a die, or I might for flipping a coin. So all of the possible outcomes. So the sample space for rolling a die, so capital S would be for sample space, and then curly brackets, and then the possible outcomes, that would be your sample space. Those are the 6 outcomes in your sample space. Now we need to define our event. So the event is, what do we want to happen? What are we looking for? What is our desired result? What would be a win? So here, our event is going to be to roll an even number. So we use the capital E for event. If you had more than one event, you might use E for one event, F for the next event, G for the next event. We started E because that's event, and then we would use the next successive letters as capital letters. So my event would be to roll an even number, and in set notation, I would put curly brackets, 2, 4, and 6 satisfy that rolling an even number. So that's what we would put for our event. I will ask for that. I believe that My Open Math asks for that as well. So let's talk about using the empirical approach to approximate our probabilities. So the empirical approach requires you to actually perform the experiment. So let's talk about rolling die. So rolling a dice, you would actually have to roll it however many times. So let's say that I rolled the dice 100 times. So we're looking for the probability. Our event is rolling even number. So our event is rolling an even number, so the probability of rolling an even number. I rolled the dice 100 times. Let us say that out of those 100 times, 48 of them were even numbers. So if I rolled the dice 100 times, 48 of them are even numbers. So that would give me, that would be 24, 12 out of 25. So 12 out of 25. We simplify those fractions. When you're doing your homework, it's going to require you to give a simplified fraction. So 12 25ths would be your simplified fraction. So you put the frequency of event. Remember, frequency is how many times did it occur. So frequency of our of getting the desired outcome over the number of trials. That's how many times did you roll the dice, or how many trials did you do? How many M&Ms did you pull out of the, or do you have total, or whatever. Okay, so let's do an example. So Pass the Pigs is a Milton Bradley game in which the pigs are used as dice. I have never seen this game. One of these, because I keep teaching this and I keep talking about it, I need to find this game. Points are earned based on the way the pig lands. There are 6 possible outcomes when a pig is tossed. A class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is on the right. So we have each outcome here. So like, for example, out of 3,939 times, the side with the dot was seen 1,344 times. It doesn't matter how many students were really rolling it. That's not really part of what we're doing. So what matters is there were 3,939 times that the pigs were rolled, and here's how they landed. So here's what we're going to do. Oh, I gotta quit doing that. So we are going to build a probability model. We are building that probability model. So the first thing I want to do is to use the to build a probability model. I'm going to figure out the probability of each of these. So in order to do that, I do, for example, 1344 over, what was it? 39. I need to have that fraction simplified. So that fraction simplified is 448 over 1313. And you can put that in your calculator and you could get that that is approximately 0.34. Okay, so the side with the dot, we do the same thing. 1294 over 3939. Put that in your calculator to estimate or to simplify your fraction. It does not simplify. That is approximately 0.33. Do this with each of them. $59 over 303. That's approximately, what is that? Uh-oh, it's not giving me my answer. Okay, I'm having issues here. Don't mind me having issues. Okay, that's approximately 0.19. So 365 over 3939. That does not simplify, and that goes to about 0.09. 137 over 3939. I apologize if you can hear my grandson being salty in the back. 0.03, and then 32 over 3939. Does not simplify. That's about 0.01. All right, so now let's look at B. B says estimate the probability that a thrown pig lands on the side with a dot. So what we're looking at here is the side with the dot. So there's about a 33% chance, because remember, to change a decimal into a percent, we multiply by 100 or move the decimal over 2 places. So about a 33% chance of it rolling on, based on our experiment, 33% chance of it rolling onto a side with a dot. So about a third. So the probability based on the empirical approach of it landing on the side with a dot is 0.33 or 1294 over 3939. So would it be unusual to throw a leaning jowler? So going back to our empirical model with our bell curve, I'm going to switch over here real quick. So I'm going to draw my beautiful bell curve here. As always, my drawings are perfect. So this is my mean. There's 1 standard deviation away from the mean, 2 standard deviations away from the mean. Remember, in order to not be an outlier, it needs to be within 2 standard deviations away from the mean. So this right here would be 95% of all of our, 95% of all of our data is within 2 standard deviations away from the mean. So this over here and this over here together is 5%. So anything in that 5% is an outlier. So going back to the other page, if a number is less than 5%, then we consider it unusual. So here we have that our leaning jowler is 0.01, so about a 1% chance of it being a leaning jowler. So that is definitely unusual. So if it's less than 5%, it is unusual. I'm going to write it right here. Less than 5% or 0.05 is unusual. All right, let's move on. Okay, so this one I'm going to have you build this probability model. So this is about how 200 people were asked their means of travel to work. So 200 people were polled, and it's a sample of 200 people were polled to determine how they get to work. So I would like you to use this data to build a probability model for the means of travel to work. Estimate the probability that a randomly selected individual carpools. Interpret the result. We'll talk about that. And would it be unusual to randomly select an individual who walks to work? So I would like you to pause this and complete this probability model on your own, and then come back and we will do it together. All right, so I'm hoping you paused it. I'm hoping you built this probability model. So let's do this together. So there are 200 people. So we write our fractions like this. Make sure you simplify your fractions if possible. And this cannot be simplified, and that's 0.765. This one is going to be able to be simplified. And that's equals 11 over 100 or 0.11. I'm hoping you can simplify this one all on your own without even using a calculator. But if you are tired, you may not be able to do that, because sometimes we have that happen. Our brains don't like to do the simple math, which is perfectly fine. That's why God made calculators, right? Hopefully you can do this one yourself as well. But once again, we all are tired. Life gets in the way. We lose our minds and can't do simple math. So if you can't, that's okay. This one will not simplify. So no need to tax your brain there. This one also will not simplify. So equals 0.035. So hopefully that's what your probability model looks like. So now estimate the probability a randomly selected individual carpools to work. So we are looking at this line right here. So if I just randomly grab someone, it doesn't say what my population is. It could be the population of it could be people in a certain town. It could be over the whole United States. I don't know what the population is. But if out of that population, I randomly selected one person, what's the probability they carpool? About 11% chance that they carpool to work. All right, so last, would it be unusual to randomly select an individual who walks to work? So let's take a look at the walks part right here. So if I move that decimal over 2 places, I get 2.5%. Because that's less than 5%, yes, it would be unusual to randomly select an individual who walks to work. If you have any questions on that, make sure you send me an email or a message through My Open Math. Let's move on. Classical method of computing probabilities requires equally likely outcomes. The classical method is just slightly different. It requires equally likely outcomes. So this means that every simple event has to have the same probability of occurring. So for example, if I roll a dice, 1, 2, 3, 4, 5, and 6, all of those are equally likely. It is equally likely to roll any of those numbers on that dice. If I pull a card out of a deck of cards, every single card is equally likely to be drawn. So if I have a bag full of M&Ms, every single M&M in that bag is equally likely to be pulled out of there. So in order to do the classical method, every event has to be equally likely. Okay, so here's my classical method. I'm going to go back to rolling dice because that's where my brain is right now. So we have if an event is equally likely outcomes, then the probability of E is like this. So let's say the probability rolling an even number. Okay, so how many ways can E occur? So how many possible ways? We know that there are 3 even numbers on a fair dice. So we put 3. How many possible outcomes? Well, way back in the beginning, we talked about all of the outcomes on a dice. There are 6 possible outcomes on a dice, so we have 1/2. So the probability of rolling an even is 50%, or 0.1 or 0.5 or 1/2. Once again, this does not require that we actually do the experiment. This is the actual real probability. So this is the real probability of something happening. It does not require you to perform the event. It's just all mathematical. It's all doing the math. It's not you actually doing the experiment. We're using our counting techniques to find the probability. Let's do some examples. Okay. So suppose we have a fun-sized bag of M&Ms. There are 9 brown, 6 yellow, 7 red, 4 orange, 2 blue, and 2 green candies. If I added all of those up, that's 30 candies. So there are 30 candies in this fun-sized bag of M&Ms. We need, as I said earlier, every candy in the bag is equally likely to be drawn out if I pulled a candy out. So if I randomly selected a candy, what is the probability that it is yellow? So once again, there are 30 candies in the bag. So the probability it's yellow. 30 in the bag. So all 30 candies have an equally likely outcome or possibility. And there are 6 yellow. So I put 6 over 30. So that's 0.2 or 1/5 or 0.2. So there's a 20% chance of pulling out the yellow. So what is the probability that it is blue? So there are 2 blue candies. So the probability of blue is 2 over 30, which simplifies to 1/15. So that probability right there is 0.067. So that's about a 6.7% chance of pulling out the blue. So we're going to comment on the likelihood of candy being yellow versus blue. So there is a 3 times more likely to get a yellow candy than a blue. We are 3 times more likely. I just realized that I forgot to talk about back here. Sorry about that. When I talked about interpreting the result, basically what I'm saying on interpreting the results, so we have individuals that carpool, so 11% chance. So it's saying that out of 100 people, 11 of them will carpool to work. That's what I mean by interpret. So if there were 100 people, 11 would likely carpool to work. Okay, sorry about that. Let's go back here. So I would like you to do this one. So you're going to compute the probability of rolling a 7. You're going to compute the probability of rolling snake eyes and then comment on the likelihood of rolling a 7 versus rolling a 2. So I want you to pause this and complete this page right here, and then we will come back. All right, so let's take a look at this. So I'm going to use blue because it'll be easy to be seen. So the probability of rolling a 7. So the 7s are on this diagonal right here. These are all the 7s. So total possibilities of rolling 2 dice is 36. So we have a probability of a 7. So there's 36 on the bottom. So I have 1, 2, 3, 4, 5, 6. 6 out of 36. So that simplifies to 1/6. So that is 0.167 approximately. So the probability of rolling snake eyes, I'm going to use a different color here. Let's use green. So there's only one way to roll snake eyes. Remember, snake eyes is 2 1s. So I have 1 out of 36. So 1 out of 36 gives me about 0.028. So what is the likelihood of rolling a 7 versus rolling a 2? You are 6 times more likely to roll a 7 than you are to roll a 2. Hopefully that makes sense to you. And if you have any questions, make sure that you send me an email or a message on My Open Math. I'll come back with 5.2.